Thank you very much for this very nice introduction and for the invitation to speak here. So here today I'll give a talk about these MTP2 distributions, which stands for multivariate total positivity of order 2, and I'll define it on one of the next slides. So I've got an interest in these distributions now already for a couple of years, and I've worked on this topic with different subsets of people that I have here and that I'll introduce throughout the talk. And so I've come to really appreciate these kinds of distributions because they're inherent in many different data sets, but I think it has really not been made use of enough in terms of modeling. And so I want to tell you a bit about the kinds of dreams that came true for me looking at these kinds of distributions, and I hope that maybe some of your dreams will also come true with these MTP2 distributions, but we'll see. So in terms of modeling, so what are the kinds of problems that motivate looking at MTP2? So here, for example, if we look at stock data or financial data more generally, you'll see that, although they don't always move exactly the same way, but stocks usually move together, right? Either they go down or they go up, but many of them will be moving together. Some will go more down and some will go more up, but they actually move together a lot. So this is a very strong form of positive dependence that is happening. Right? It's, this comes about because you have some very strong market variable, some latent market variable that are underlying the stocks, and so this will make them move together. So this is a very strong form of positive dependence that you see here. Also, we work on a lot of biological applications, which I won't talk about a lot today, but if you look at gene expression data, for example, you'll also see that many genes move together, up and down. And this comes about because, you have the packing of the DNA that was spoken about before that we work on together with Shiva's lab. You have the packing of the DNA, and if you have a transcription factor that comes in and these genes are close together, they can be co-regulated. So they will all go up or down together, just given by the spatial organization of the DNA inside the cell nucleus. So in many different applications, and we'll see some others later on as well, like psychological data, etc., you'll see that variables go up and down together. Okay, so they show these very strong form of positive dependence, and so we would like to be able to model this kind of positive dependence. And so MTP2 is the strongest form of positive dependence known right now. Until now, it has only been studied from a theoretical perspective, but what I would like to kind of highlight today is that I think it is very interesting to take it into account also from a modeling perspective. Okay, so let me define what this actually is. Okay, and you'll see it's a very strange definition, which doesn't seem to have anything to do with data science. So this is just a definition of what MTP2 is. Okay, so as I said, distributions can be MTP2. And the definition of a distribution to be MTP2 is if the density function, and it can be continuous or discrete, doesn't matter, if the density function satisfies these inequalities here. Okay, so for any sample, so you have to take any 2 points in this sample space, and then what you want is that the density function at x times the density function of y is smaller or equal to the density function at x min y times the density function at x max y. Okay, so something super strange. Why would anyone ever want to study something like this? So note, if you know supermodularity or submodularity, right? If I take logarithms, so if the density function is everywhere positive, I can take logarithms, and then you get exactly log supermodularity, right? So then I'll have a plus here, and I'll have a plus here, and that's exactly supermodularity. Okay, so why would anyone want to study like log supermodularity for density functions? Well, as I said, the motivation was completely theoretical, okay? So this was not introduced to do anything in terms of data analysis. It was really introduced in probability theory just to study positive association. Okay, so what is positive association? So a random vector is positively associated. If and only if, the covariance, when you take 2 non-decreasing functions, it always has to be larger or equal to 0. Right, so this has been a super important property in statistical physics, etc., right? Probability theory, and people wanted to study this, but it's very difficult to check, right? This property, I have to check it for any 2 non-decreasing functions. And so what the celebrated FKG inequality tells us is that, and this is why it was actually introduced, MTP2, is because MTP2 implies positive association. Okay, so it's the strongest, and it in fact implies all known positive dependence properties. But this is really why it was introduced, right? This is very hard to check. MTP2 is easier to check because you only have to check it for points in your sample space, right? And in fact, it implies positive association. Okay, so it was really introduced just for its theoretical properties in order to study positive association. Okay, so that was the motivation. Now let me just tell you a bit about the well-known properties of MTP2 distributions. So it has, I'm saying all your dreams, or your dreams may come true with MTP2. So it has all of these nice properties of Gaussians, basically. Okay, so these are some very well-known old properties, right? MTP2 has been studied for a long time now. So for example, it is closed under marginalization. Okay, so if I have an MTP2 distribution, I take a marginal, it's still MTP2, like a Gaussian, right? If I take a conditional, still MTP2, whatever you want to condition on, it will always remain MTP2. Another property of Gaussians is that if I have a 0 in the covariance matrix, it already implies independence, right? Super strong property. Again, you have it for MTP2 distributions. And you have some other properties, but one I should point out that you don't have, okay, which you have for Gaussians. So it's not closed under convolution. So this is one of the things that might not come true with MTP2, okay? So, but it has, and these properties have been known for a long time, so it has all these super nice properties, right, that you would want a distribution to have.
So, were you implying that just the definition you gave on the previous page implies all this?
Exactly, yes. So MTP2, if X is MTP2, then it is in fact, whenever you take a marginal, it's again MTP2. If you take a conditional, it's again MTP2, and MTP2 itself just implies this as well. Okay, so and we will see it's a super strong property. That's why, probably people have never thought about using it for data science because, why would this ever be true, right? That you have such a strong property, but I would like to argue that it is actually intrinsic in many different data sets. Oh yes, so here, this is min and this is max. And
minimum of x and y and then maximum of x.
Oh, correct. Okay, so x and y, so say you're in RD. Let me do it in RD. So I mean entry-wise minimum and entry-wise maximum. So if we do it in R2 and I give you 2 points, I don't know, say these are my 2 points in R2, then I mean entry-wise minimum and entry-wise maximum. So if this is x and this is y, this is x min y, this is x max y. And so what I mean is the density at x times the density of y has to be smaller or equal to the density of x min y times the density of x max. Okay, so for example, like a tent function, right, would be where this guy here comes out and it's a tent going down like this, would satisfy MTP2 properties. Okay.
The generic properties, do they need that this is a subset of R or any total order space or something?
Totally ordered, exactly, that's all I need. I need to be able to define min and max. Yeah, and so you can actually define this very generally, yeah. So I don't need RD. Okay, so that's the definition of MTP2. Just to give you a bit of intuition for why I think it is a very nice property for data science, let me look at a particular application that people don't like, right? So when you do analysis of data, there is something known as the Yule-Simpson Paradox, which you're probably all familiar with. It just says that in a data set, 2 variables can be positively associated, but once you condition on a 3rd variable, they suddenly become negatively associated. Right? Something that is really, really disturbing when you do data analysis. And here is an example, right? These are the death sentences that happened in Florida in these 6 years here. So if you just look at this data, and I did the analysis for you before, so here, so you will see that more white murderers got the death sentence than black murderers. If I just don't condition on any variables, but now suddenly if I condition on the skin color of the victim, and I'll look at separately the black ones or the victims that were white, you'll see that it actually suddenly changes around. And in both cases, more black murderers got the death sentence than white murderers. Okay, so this can happen. I mean, there's other very interesting cases like Berkeley admission rates, etc. If you look at every department, right, there was more females that got admitted than males. But if you look at the whole school, there was a clear bias in terms of less females being admitted. Right? There are many, many examples like this. And this is both for real representations of the data, right? We're not lying or anything. It's just that associations can suddenly change when you're conditioning on a 3rd variable. And under MTP2, something like this cannot happen. Okay, so what MTP2 is a super strong form of positive dependence that no matter what you condition on, you're still positively dependent. So that's another nice property when you're thinking of data science. Right? So you cannot suddenly have signs or associations change their sign. And let me maybe go through why this cannot happen under MTP2. Okay, so let's just, again, just as a reminder, what is the definition of MTP2 that I have here? So let's just look at it, what it means for binary distributions, just to get a bit more intuition for this kind of constraint. So let me look at binary distribution, just a two-dimensional binary distribution. Okay? So what does it mean to be MTP2? Well, I have to go through all possible x and y's in a two-dimensional binary setting. So that's 0, 0, 0, 1, 1, 0, 1, 1, right? And I just have to go through all possible such inequalities. And if you just write them all out, you'll see that there's only one non-trivial one, namely this one here. Because if you, for example, take, I don't know, P00 times P01, I have to take entry-wise min. So that gives me, again, 0, 0, right? And entry-wise max, which gives me 0, 1. Right? So this is a trivial inequality. So if I just get rid of all of the trivial inequalities, you'll see that there is only one left that is non-trivial. Okay? So that's what it means for a binary two-dimensional distribution to be MTP2. And this is what it means to be positively associated, right? And so if we go to the three-dimensional binary distributions, and then I look at the conditional, you'll see that Yule-Simpson's paradox cannot happen. So here what I did is, let's look at three-dimensional binary distribution. Again, I'm writing out all non-trivial inequalities, okay? Particularly, you'll see that for three-dimensional binary distributions, there are already 9 non-trivial inequalities. So it's clear that this is a super strong constraint, right? It will explode once I go to higher and higher dimensional binary distributions. But one thing, if you just write down the conditional odds ratio, right, where I have to condition on, say, the third variable, you'll see that this always implies this. Okay, so this being positive will always imply that this is positive as well. So that means that you can never have a Yule-Simpson's paradox. So it really just follows from the definition of MTP2 in the binary setting. Okay, so something like this example here that we had cannot happen. Okay, whenever you have positive association, it will remain positively associated no matter what you condition. Okay, so this is what it means for an MTP2 distribution to be, for a binary distribution to be MTP2. So as you see, it's super restrictive, right? And so we don't know actually a formula for the volume of all MTP2 distributions. However, in the three-dimensional case, we can actually compute it, and it is about 2%. But of course, so it's always full dimensional, but I really don't know how bad it becomes. Okay, so four-dimensional binary distributions, I cannot compute the volume, or we don't know how to compute the volume of all MTP2 distributions. But it's definitely super restrictive, right? So, but I still want you to care about it. And why is it? Well, I can actually give you examples of real data sets that are MTP2. Right, it shouldn't be possible. I mean, it's not the case that I went through, hundreds of data sets, or in this case, 50 data sets to find one that is MTP2. Right, but here I'm giving you an example that is actually MTP2. So this is a particular disease syndrome in pregnant women. These are, the 3 symptoms that these women have. This is the real data set from this study. And if you just plug in these numbers in here, you'll actually see that they just satisfy all of these inequalities. Okay, so that's kind of crazy, right? So these data sets actually happen in practice. And so the question is, why do they happen, right? And then, of course, since they happen, we should probably also take this into account. So that's in the discrete setting, just to get a bit of intuition for what MTP2 is. Let's maybe also look at a continuous distribution. Here we had a discrete distribution. Let's maybe look at a Gaussian distribution and see what does it mean for a Gaussian distribution to be MTP2. Okay. So here again, just so that we don't forget the definition, right? This is again the definition of MTP2. And now, as I already said, so Gaussian distribution is strictly positive, so I can actually take logarithms everywhere. Okay, and so then this is just writing down the definition. It's the same as supermodularity. And you can actually check for yourself if you write down, the Gaussian density function and you check when does it actually satisfy this. You'll see that it satisfies MTP2 if and only if you look at the parameters of the Gaussian distribution, so the inverse covariance matrix. And you need that all of the off-diagonal elements of the inverse covariance matrix are smaller or equal to 0. Okay, that really just follows from just writing down the definition of the density and checking when is it supermodular. Okay. So why does this have anything to do with positive dependence, right? So I'm saying the entries of the inverse covariance matrix have to be smaller or equal to 0. But remember that the entries of the inverse covariance matrix, they're the negative of the partial correlations. Right? So this really means that all of the partial correlations are positive or non-negative. Okay, so we have like this minus sign that creeps in. So this all makes sense, right? So this means that all of the conditional dependencies, they all have to be positive. Okay. So this is what it's known as an M matrix. M stands for Minkowski. So one of the students defined matrices in linear algebra, matrices that have all off-diagonal elements smaller or equal to 0 as Minkowski matrix. That's an M matrix. Okay. And now just a very simple linear algebra fact. So if I have a matrix, M, where all these entries here are smaller or equal to 0, and on the diagonal, of course, for it to be positive definite, I need to have larger than 0 entries. And you take the inverse of this matrix, then you'll actually get that all entries are larger or equal to 0. And of course, on the diagonal, I have again. This is just a simple linear algebra fact. Okay, a very nice linear algebra fact. So if I have an M matrix and I invert it, all of the entries are going to be larger or equal to 0. So this means that the covariances are all larger or equal to 0, which is good again, right? That's positive association. All covariances are larger or equal to 0. And just again, a linear algebra fact, just because you see a matrix like this, doesn't mean that the inverse is of this form. Okay, this is really strict. It goes only in this direction. This is, in general, not the case. It's, again, a nice linear algebra fact. So this is for a Gaussian what it means to be positively associated. This is for a Gaussian what it means to be MTP2. MTP2 is much stronger than positive association. Okay. So, but again, when is the last time that you saw a positive definite matrix where all entries off diagonal were smaller or equal to 0? That's super strong constraint. But again, I would like you to care about it. So let me actually show you an example of a distribution that actually satisfies MTP2. Okay, so if I were just to sample uniformly correlation matrices of size like here, 5 by 5, then only less, and here I really don't know the volume, okay? So I just sampled 10 to the 6 many correlation matrices and none of them were MTP2. Okay, I don't know the exact volume of how many of them are actually MTP2, but it's certainly smaller than 10 to the 6. Okay, so it's, I think, super surprising that I can give you a real example, right, of an MTP2 matrix that actually happens in practice. Okay, so this one is just, if you look at the 2016, and all I did is I Googled small covariance matrices finance. This is the first one I got. Okay, and I just checked. So I knew that in finance, they're always positive. They usually give the sample covariance matrix. All of them are larger or equal to 0. In general, as I said, it's not the case that just if I inverted, it's MTP2, right? This is a much stronger constraint than this. But it just so happens that this one here is actually MTP2. It shouldn't happen, right? It shouldn't happen. I mean, they're so rare, it really shouldn't happen that I can actually find these matrices.
So can one quantify what kind of inequalities the positive, there must be some additional inequalities the positive covariance matrix must satisfy, which imply MTP2?
So I only know it like this, that once you invert, so what this means is I can have all cofactors here, right? So I can quantify it based on this matrix, just as an algebraic constraint on all cofactors.
Only at that level.
But only at that level, yes. Yeah. So it would be really nice. So I can actually, okay, so this volume we can compute for 3 by 3. Because it's a hard integral. Okay, for physicists, it might be an easy integral. We are not used to computing these integrals. So I come from an algebra background. So I'm not used to computing integrals over the positive definite cone with constraints on the off-diagonal elements. So to me, it's a very hard integral that I would have to compute, right? I would want to just compute the integral over a positive definite cone with all off-diagonal entries being smaller or equal to 0, and I would like to know what this volume is. And so I can only do it for 3 by 3 matrices, but it would be really nice to know what this volume actually is. In particular, as you're asking, as compared to this volume, right? Not just this by itself, but actually in comparison to this volume. Okay, so why is it that I can actually find these examples? So this is why we believe, and this is how we were able to find these examples and where we were looking. Sorry, is that it turns out that whenever you have latent tree models, we can prove that they're MTP2. Okay, so in particular, think of a factor analysis model where I have, is this me doing something? Okay, let's try this. Okay, let's try. So in particular, so if you have a factor analysis model where you have one latent factor, say, and then these are all of your observed variables. And think of the finance example, right? This is why we were thinking about finance. If I have a latent market variable that I don't get to observe, but it has a very strong effect on all of the stock prices, then you expect to see MTP2, because we can prove that whenever you have a latent tree model, and I should maybe explain what I mean here by up to sign, then up to sign, we will always get MTP2 distributions down here. Okay, now why up to sign? Let me go back to this syndrome. Right, so this is exactly the same example, right? So here I have some disease that I cannot directly measure, but I can measure these symptoms down here. Right, then I expect it to be MTP2, because if this model fits well, then I can prove that it is MTP2. And why up to sign? Well, because these symptoms down here, maybe if I have a low value, it means that I have a disease, or if I have a high value, it means that I have the disease. So I might have to flip the signs, right? Because I can measure something, I can just change the sign, and it means that I have the disease. So that's why I mean here that it's up MTP2 up to trivial signs flips of like to making things, here have positive signs. I need to measure stuff. I need to measure the symptoms so that, when I have a high value, it means that I have the disease. Like IQ tests, again, is another example where you'll always get to see MTP2 distributions. But again, I can ask the question so that if you have a high value, it means that I have a high IQ, or if I have a low value. So I'll have to make all of the questions be of the same sign. But whenever you have any latent tree model, then in fact, we can prove that it is MTP2. Okay, so this is how we found these examples. This is what we were just looking for. So somehow, many people are happy, and there are many other examples, but many people are happy to model with trees. And so what we're saying here is if you're happy to model with trees, well, you're implying MTP2. MTP2 is a weaker constraint than a tree model. So let's see what we can actually get out of just modeling with MTP2 instead of trees. Okay, MTP2 is probably implied also by many other things, but we just don't know. Okay, it would be nice to have a nice characterization of what actually implies MTP2. We have like some list here, but this is kind of what we've been working on, like looking for trees or tree models. Okay, so in particular, if you look at phylogenetic data, you'll always see MTP2 distributions. Yes?
The ferromagnetic
Ising model. Mm-hmm.
Is there some physical way of looking at the line?
So we'll actually be looking at Ising models as well on one of the next slides. So this is basically just from the definition. It's like in the Gaussian setting, these thetas have to be smaller or equal to 0. If you just write down the Ising model, it's again a quadratic exponential family. It's exactly the same. These thetas have to be smaller or equal to 0, which is the same as ferromagnetism. So it's equivalent for an Ising model to be MTP2. It means that it is ferromagnetic. Ferromagnetic, again, is this strong form of positive dependence, right? That it makes like all of these spins be upwards. Yes. And there are many other examples here. These were the examples that were already known before, and this is what we developed a bit more in terms of why it is important for modeling. Okay. So what do I want to talk about? So I want to talk about, well, what does it help you to actually assume MTP2? Okay, so for modeling, so I told you, well, it's a super strong constraint, but it seems to be relevant because I can give you many examples that are actually MTP2. And now what I'd like to show you is that for modeling, what are the consequences of actually just putting MTP2 as a constraint when you're actually modeling. And I'll do that first in the parametric setting. So parametric setting meaning, I'm happy to assume some distribution like a Gaussian or an Ising model, and I'll talk about Ising models, okay? But sometimes you don't want to make any parametric assumptions, right? Sometimes these are just too restrictive, and I just want to go completely non-parametric and just say, okay, so what does it mean to do density estimation under MTP2, for example? MTP2 is a shape constraint, as we just saw here, right? So I could try to do it just completely non-parametrically, not assume Gaussianity, not assume Ising models, nothing at all, just do that. So those are the two things that I want to talk about. So what are the implications of actually putting the MTP2 constraint explicitly on the problem that you're trying to solve? And I'll show you that it actually leads to a lot of very, very nice properties. Okay, what am I not talking about? Right, everything is about positive dependence. I'm not talking about negative dependence. That's a whole different topic. And I do want to say that it's not symmetric. So it's not that because I tell you everything about positive dependence that you can also now say that you understand negative dependence. Okay, negative dependence is a whole different story. And why is it the case? Because something interesting happens. So negative association, I define it in the same way, right? The covariance matrix for any two non-decreasing functions is smaller or equal to 0. So now we could hope that the same as MTP2, right? MTP2 implies positive association. Well, maybe I could just turn around this inequality here, right, for MTP2. So I just turn it around to have larger or equal to 0. But unfortunately, it is not the case that this inequality implies negative association. Okay, so that's really unfortunate, right? So for MTP2, I have that, right, P of x times P of y smaller or equal to P of x min y times P of x max y. But this implies positive association, right? But if I turn around here, this inequality, it does not imply negative association. Okay. So that's unfortunate, okay? So the story is really very different in terms of negative association. And it was only very recently actually defined what is the correct property, right? Again, you have the same problem that negative association, very, very difficult to check. So you would like to have something like this property here that implies negative association. And it was only recently defined, and in fact, only in this discrete setting. So the continuous definition is not yet known of what it would imply negative association. And so these are known as these strongly Rayleigh measures. So that's the correct definition of what you have on this side to imply negative association. But in the continuous setting, nothing is known yet. Okay, so this is a really hard story. But again, very recently, negative association has also been used in data science. Okay, in particular in machine learning, there are more and more people who actually look at negative association. And what kinds of applications is it important? Well, if you look at recommendation systems, right? There you want it to be diverse. So if I have already bought a mobile phone, well, I'm very unlikely to buy one more next week, right? So you want that the probability of you actually getting to see in your recommendation system, for example, on Amazon, another mobile phone when you have just bought one should be small. But instead, maybe if you bought a mobile phone, then you might want to buy a hat, etc. Right? But again, the probability if you have already bought a hat to buy another one should be small. So when you look at recommender systems, then negative association is something that people have looked at as a very important constraint. Same thing when you have huge matrices, right? Matrix sketching is just figuring out some columns to keep. Well, you want to keep the columns that are as different from each other as possible, right? So again, you want negative association in order to get a diverse set of columns that you want to keep. Or for example, in neural network sparsification, I only want to keep the neurons that actually save different kinds of information, etc., etc. Okay? So in these kinds of applications where you want diversity, that's when negative association or negative dependence or these strongly Rayleigh measures have actually been used. Okay, but just notice that it's a very different story than positive association. It's not symmetric. Okay, it's not the case that I can just turn around all the signs and I'm happy to go. Okay, so that's all I will say about negative dependence. And if you want a nice tutorial on negative dependence, Stephanie Agelka and Suvrit Stra, they have a very nice tutorial at NeurIPS last year, which is online available. Okay, so let's get back to positive dependence, and I'll first talk about the parametric setting. Okay, what can you gain by adding MTP2 to the parametric setting, in particular Gaussian or Ising setting. Okay. So in the parametric setting, just to generalize Ising and Gaussian, let me look at exponential families. Okay. So these are density functions that are of this type here, where these are my parameters. These are the sufficient statistics. This is just a normalizing constant. Okay. So in particular, a Gaussian or an Ising model is such a case, right? And exactly, if you look at this function has to be supermodular, just means that this parameter has to be negative, smaller or equal to 0. So that's why it's the ferromagnetic Ising model, or it's in the Gaussian setting that the inverse covariance matrix is smaller or equal to 0. Okay, so what does it mean for an exponential family to be MTP2? Well, it's actually a very nice constraint. So it's a constraint on the space of canonical parameters. So it's a constraint on these thetas, right? We already know it in the Gaussian and Ising case, as I said, it's this non-negative orthant, right? All of the entries have to be smaller or equal to 0. Right? So this is the constraint for Gaussians and for Ising models. And what this theorem says is that this holds generally. That's always a convex constraint. Okay, so this MTP2 constraint is always a convex constraint, meaning that if I do parameter estimation, for example, maximum likelihood estimation, it's always a convex optimization problem. Okay, so it can be solved nicely in many cases. Okay, so it's always a convex problem, and in fact, if I have quadratic exponential families like the Gaussian or the Ising, what you also see here is that it's a polyhedral cone. Right? And this is true in general. So quadratic exponential family, whenever here I have just a quadratic function of my data, so t of x is quadratic in the data, then always you can show that this is always a polyhedral cone, like you see here in the Gaussian setting or the Ising setting. And these faces of the cone, they correspond to conditional independence relations. Okay, so they correspond to statements like x independent of y given some random variable z. So like in the Gaussian setting, right, if I have one of these be 0, if you have the inverse covariance matrix, you have a 0 in there, it means that x is independent of y given everything else. And this is true in general for any quadratic exponential family. So this already tells you that it's a very nice implicit constraint, right? It implies that I have a lot of conditional independence relations. Because when you do, when you have a data point, often it's not MTP2 itself. So what happens when it's not MTP2 and I do maximum likelihood estimation? Well, I'm going to project it to the cone of parameters. Right? And so if you project to the cone, well, you'll land on one of the faces, but on the faces you have conditional independence relations. So you actually just get sparsity for free. Okay, so it's a very nice implicit regularizer where you just get sparsity for free. So whenever I have a data point, it's not inside the cone, I'll project it, and all of the faces correspond to conditional independence relations. Okay, so again, it hints at the fact that it's like very, very nice when you do data science using this constraint here for any exponential family. Okay. So in the Gaussian setting, as I said, so here is maximum likelihood estimation in the Gaussian setting, right? This is the likelihood in the Gaussian setting. This is the MTP2 constraint, so all off-diagonal elements are smaller or equal to 0. Nice convex optimization problem. This is concave likelihood subject to these linear constraints. Nice convex optimization problem. I can write down its dual using, for example, you can solve it for very big problems. So this is what it means to do maximum likelihood estimation in a Gaussian setting under MTP2. And you get sparsity for free, right? I will get many zeros in here if I'm not already MTP2. So the standard way of doing it is adding L1 penalty. So standardly, people would maximize the likelihood subject or plus L1 penalty just to make it sparse. But I'm just telling you from the previous theorem, well, you'll already get something sparse. So this is really an implicit regularizer. Okay, I'll just get sparsity for free, so interpretability for free. So what is another reason for using L1 penalty? What is the standard way of doing it, right? Graphical lasso is just L1 penalty. Well, the reason is that this maximum likelihood problem, it goes off to infinity if I don't have enough samples. Okay, so in particular, if S here is not full dimensional, so it has not full rank, well, then this thing here goes off to infinity, and the problem is ill-defined. So people add L1 penalty so that I can also do maximum likelihood estimation where I have few samples. Okay. And in fact, under MTP2, you can show that you just need 2 samples. Okay, and then this constraint here will already make the problem well-defined. So just 2 samples, and this MLE, this function here, will not go off to infinity. And this is a much stronger result than what they get for L1 penalty, right? Because under L1, it still depends on the dimension of the problem. Here, just 2 samples, independent on how large your covariance matrix is, independent of how many variables you have. Okay. Which is intuitive because it's a super strong constraint. But, so it is a strong regularizer, right? But we saw many examples which are actually MTP2 and where it makes sense to actually use MTP2 as a regularizer. So this is what you gain, okay? You get sparsity for free and you can actually apply it in a very, very high dimensional setting. And so there is an original proof by Slavsky and Hein. And if you use some connections to linear algebra, in particular to ultrametrics, this actually just follows in like 3 lines. So this is a very simple proof. And also for the high dimensional setting, using graphical lasso, right? What they do is they have this log likelihood minus lambda times the L1 penalty, right? But you always need to choose lambda correctly so that it gives you the correct estimator, so that it's actually consistent. Now, as you see here, we don't have any tuning parameter, right? There is no dependence on choosing lambda correctly. So usually for graphical lasso, you need to tune your parameter in order to have consistency guarantees. Here, you don't need to do anything. And you can actually prove consistency of these algorithms. So that's in the Gaussian setting. And we have the same results also for Ising models. So if you're thinking of ferromagnetic Ising models, the standard way, when you have an Ising model to compute the MLE is this iterative proportional scaling. We have the same algorithm also for Ising models. So we can actually compute it for very high dimensional Ising models. We can compute the MLE for ferromagnetic Ising models. And in particular, we also have the same results as on the previous slide. We know when the MLE exists. So in Ising models in general, you need huge amounts of samples, right? You need to have seen every combination of all of your spins at least once, right? So that's why you need at least 2 to the many variables, many samples, right? V is the number of variables for me. So for the MLE to exist, you need to have seen every combination of spins, right? But under a ferromagnetic Ising model, what you can prove is that you only need to have seen, if I have an Ising, let me take the complete graph. So no constraints. I need to have seen at least every combination of signs. So for any 2 variables, I need to have seen the combination 1 minus 1 and minus 1, 1 here. Okay. So in particular, if you just write that out, that tells you that we only have to have seen V many samples. So as many as you have variables. So we went from 2 to the V many samples for existence of the MLE to just V many samples for the existence of the MLE. Okay, so it's very similar as in the Gaussian setting. So it's, again, when you add this ferromagnetic constraint, or this MTP2 constraint for Ising models, it's a very nice constraint for high dimensional modeling. You need very few samples for the MLE to even exist.
So I suppose it in terms of the Ising model. So if you take the 3D Ising model, the fact that there's a phase transition and calculating the critical point and blah, 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 because I know it's not analytically done. Are you saying this can be done? I'm not.
So what I'm saying is so I have an algorithm for computing the likelihood, the maximum likelihood estimator.
That's like the most probable state.
Which is the most probable state, exactly. So this I can do, and I have an algorithm for doing that, which is the same as iterative proportional scaling. So I'm just fixing all of the, yeah. And I'm telling you that the MLE, so usually it goes off to infinity, right? So when I don't have enough samples, it usually goes off to infinity. So just this additional constraint tells me that if I just have 3 samples that are well chosen, this is actually going to exist. So in general, here I would need 2 to the 3 samples, right? I would have to have seen every state at least once. Now I'm telling you I can actually get I can already do it with just 3 samples. And it's going to be all well-defined. Because ferromagnetism is such a strong constraint. And I'll have a data example, actually, where I'm really running this.
I was just trying to say, to tune one of the parameters, the system undergoes a phase transition. So in the sense, the maximum ordered state is a disordered state, IT, and a ordered state. So that comes out here?
So here I'm already putting, it's like in the Gaussian setting, I'm putting on the constraint that it has to be ferromagnetic. So I'm doing parameter estimation under that constraint, right? I'm not tuning the parameter in that sense.
No, I think he means the coefficient. There is a positive ferromagnetic coefficient, but as you tune that coefficient,
you
undergo a sort of a transition. But that's in this thermodynamic limit.
You're looking at the external field? Is that the coefficient that you mean?
The coupling coefficient, J.
Oh, that's exactly these parameters, right? So these are exactly these are the J parameters. So I'm putting on, so this is exactly the same. So I'm doing maximum likelihood estimation under the constraint that all of these J's have to be smaller or equal to 0. Exactly. And I'm not, right? I'm not putting any other constraints other than it is ferromagnetic. And now I'm just solving this optimization problem under the constraint that J is smaller or equal to 0. In general, this optimization problem will go off to infinity if I don't have 2 to the v many samples, right? If in S, you don't have 2 to the v many samples in the sample covariance matrix or your second order moments. So just me constraining the optimization problem to be in this J, in this negative orthant actually makes it really, really nicely behaved as an optimization problem. And let me actually maybe go to the data example and then we can discuss this. So you get all these nice properties, right? In the parametric setting, you just get them out for free, just by putting in MTP2 as a constraint. Okay. So what about non-parametric, which is what I had here? So in the non-parametric setting, so I don't want to put on any constraints that is Gaussian or Ising or whatever. I just want to directly do density estimation, okay? I just give you some points, and you tell me what is the most likely density that these points come from. And people have studied this under different kinds of shape constraints. So what I want to do is the following, right? So I just give you points in Rm, and I say, well, just maximize the likelihood directly, okay? From these points, just maximize the likelihood of seeing the points. So that's just optimize this problem here over all possible densities. So that's a infinite dimensional optimization problem. Right? So I give you points in R2. I'm telling you, well, just maximize the density function so the probability of seeing the data for any density in R2. So that's a infinite dimensional optimization problem. And now I'll look at the constraint that it's MTP2. Okay, so if I don't have any constraint, then this here is optimized by just pointing point masses onto your points, right? So that's not very interesting, right? So if I have, so if I just have some points, and you just maximize the density function over these points, well, then I'll put point mass here, point mass here, point mass here, right? It's not a very good estimator. I mean, you're like 100% sure that whatever next sample comes out, it will land on one of your points. So that's why people put all of these shape constraints on top of it to just make sure that, I don't want to get the trivial estimator. I don't want to have point masses on my points. Okay, so I'll put shape constraints on it. And so all of these are things that have been studied, but MTP2 is one that hasn't been studied. And unfortunately, you can show that even if it's MTP2, I'll still have point masses on top of it. So it's not strong enough for actually getting rid of this property. So I need to add one more constraint. And so out of this whole list that people have studied, we just chose log-concavity as a first one to study, but you could, take any one of them, monotonicity, whatever you like to do. Okay, so why log-concavity? Well, this MTP2, as we saw when I take the logarithm, it's super modular. So this is, after taking the logarithm, it's concave. So they seem to be nicely working together from a geometric perspective, right? I have, after taking logarithms, I want it to be supermodular and concave. But, nothing tells me that I couldn't have looked at anything else. This is just the first part where we started. Okay, you have to start somewhere, so we started with log concavity. Also, it's actually the one that is right now has, so log concavity is like, is used, I mean, there's a whole lot of literature on log concave non-parametric density estimation. And it started with this Kuehl, Samworth, and Stewart paper in 2008. And now, in the statistics literature, there is a huge amount of papers in this area. And this is kind of the amazing fact. So I have here my samples in 2D. Okay, and I'm solving this infinite dimensional optimization problem, right? I'm maximizing over all possible density functions in 2D, subject to the constraint that it has to be log concave. And so what they proved here is that the MLE, so the optimum of that optimization problem, is always a 10th function. Okay, so a 10th function is the smallest concave function where you put your 10th poles somewhere. Right? I put my 10th poles, I just put the smallest concave function over it. And so why is this such an amazing result? Well, it says that this infinite dimensional optimization problem that I have here, right, without this, just log concavity, this infinite dimensional optimization problem can actually be turned into a finite dimensional optimization problem, right? Because a 10th function, well, all I need to do is optimize over these 10th pole heights. So instead of solving an infinite dimensional optimization problem over all possible functions, all I'm going to do is solve a finite optimization problem where the dimension is the number of samples that you have, just to optimize over these 10th pole heights. And if you solve that, then you already have the MLE. So this is pretty amazing, right? So infinite dimensional optimization problems can be turned into a finite dimensional optimization problem once you know that your MLE is always a 10th function. And so the question was, well, do we have something similar under MTP2, right? Do we also just get a 10th function out? And in fact, so what you can also show here is that it's a convex optimization problem. So not just finite dimensional, but also convex. So you can actually solve it efficiently. And it turns out that, let me actually go here. Under MTP2, we also have something similar, at least in dimension 2, or in the binary setting. So we also can solve it as a finite dimensional optimization problem. We also know it is a 10th function. And in fact, again, we have a similar result that we need very few samples. So for this optimization problem to be well defined, now we just need 3 or more samples. So remember, so for log concavity, they need dimension plus 1 many samples. So again, dimension is gone. We don't have any restrictions on the dimension. So independent of dimension, we need just 3 samples. And also remember the Gaussian setting, right? Gaussian, we needed 2 samples. So now completely non-parametric, I don't care about the distribution, we just need 3 samples. Okay, so again, it tells you that it's a very strong constraint. And if I show you how it looks like, so this is when I do non-parametric density estimation, I give you 50 points. We just sampled them from a standard Gaussian, because a standard Gaussian is MTP2 and it is log concave. So if you just compute the density estimation, the density estimator under just log concavity, this is the function you get. If you compute it under MTP2, this is what you get for just 50 samples. Right, and this already shows this looks very much like a Gaussian, right? So just adding, this is definitely not like a Gaussian. So just adding this MTP2 constraint, which is super restrictive, that's true, but just adding the MTP2 constraint already with very few samples, you already get a very, very nice density estimator. So you can actually do this just completely non-parametrically without assuming Gaussianity or Ising models, etc. So let's actually look at a couple of applications. So here, let me talk about the Ising case a bit more. So here I'm looking at a psychology study where there are 16 binary variables related to 2 different disorders. These are psychological disorders that this psychology study here and multiple papers that followed it have studied. And so these are the 16 variables that people have measured. And here I have these symptoms, how many? I have 9,000 individuals, but most of them have no symptoms at all. Okay, so this is a contingency table of size 2 to the 16, right? So it's binary of 16 variables, so it's a table of size 2 to the 16. Most individuals are in just 1 cell, so most cells are empty, right? Most combinations of symptoms are empty, so you couldn't just assume Ising model and compute the MLE. The parameter estimate would just not exist. Right? Likelihood just goes off to infinity, there is no parameter estimate. However, that optimization problem, if I assume it is ferromagnetic, which makes sense in this case because again, it makes sense to assume some tree like this, right? Because I have some disease, some psychological disease that I'm trying to measure with these variables. So I'm just going to assume ferromagnetism. I have an algorithm for actually computing the Emmy, and it actually exists because it's such a strong constraint, right? So that's what you gain, right? You couldn't do anything before, and that's why people, actually this is just psychology, they didn't do anything with data, right? Because you couldn't fit anything. You didn't have any constraints enough to actually get a parameter estimate out. Now under ferromagnetism, you can actually do it quantitatively, right? Before they just went in and they said like, oh yes, we have these two diseases, and we know from psychological prior knowledge that there is actually two diseases, and these variables here have to do with this disease, and these variables down here have to do with a second disease. But if you just do it using the ferromagnetism as a constraint, you actually just get it out. Okay, we get exactly out what these psychologists have been thinking, and in particular, we get this thing out, the star graph, which they called in the paper something, the causal skeleton. You just get it out quantitatively. Right? And we get out these different edges here are exactly the only edges that we get out are the edges between these bridge variables. So there is concentration, which appears for this disease and for this disease. There is the sleep variable, which appears in both. And there is this fatigue variable, which appears in both, and we just get it out. Okay, so all these bridge variables actually just come out quantitatively. So we just get these highly interpretable results. So this is when you just look at the correlation structure. This is when you actually look at this J variable, right? Which now we can actually estimate. Here's in finance. So here we applied the Gaussian setting to the financial portfolio selection problem. So this is the standard data set that, if you want to publish something in a financial econometrics paper, apparently this is the data set that you have to show that your estimator works. So we went through this effort and actually got this to work, and we were pretty surprised. So this is the baby problem that people usually solve first. So you want to just choose the portfolio that minimizes the variance. Okay, so this is a baby problem where we're not looking yet at the gain of like how much money you're actually going to make. You just want to minimize the variance. So you want to have a small value, right? So these are the standard ones that people use in finance. And so the smallest one is the best one. And here you see that we actually have in many, many different settings. So this is the number of variables. This is the number of samples in finance, right? The number of assets is the number of variables. The look back period is the number of samples. And you see that it actually does surprisingly well without, MTP2, we didn't introduce it to do finance, right? These are estimators that were introduced for financial applications. So you can actually do very well. And this is a pretty surprising result. I started to like finance because it's very easy. So there is a real measure to say when you do better than others, when you gain more money, which I never thought about. But before you always have to do all your simulation studies, and everyone will say like, well, it's just because you chose this measure that you'll do better than others. Here you actually know when you do better, because all you look at is the average returns and the standard deviation of the returns. And this is how they measure that you do well. I'll get to that. And here, we were pretty amazed. I never thought that this would happen, that just by adding MTP2, you actually do better than than these estimators that were introduced just for this topic. Yes?
Yes, so this is the log-concave assumption.
And so this is Gaussian assumption. So here we did the parametric one. And so that is already log-concave. Yes?
How does it compare with log-concave? Usual log-concave Gaussian with the log-concave.
Okay, so that's usual Gaussian. We didn't show it on here. We have it in the paper. So just Gaussian, they use L1 regularizer. So it does much worse than this. Yes. Because it doesn't take into account that, in finance, there is a strong market variable, right? You should take it into account because, yeah. But this is more general than a factor model, exactly. So that's why I actually expected that something like this will do better. So this is this with these 5 Fama French, whatever factors, which economists actually came up with 5 factors that they believe are important. But MTP2 is a weaker constraint than that, right? So this factor analysis model implies MTP2. So MTP2 is weaker, it's more general. And so maybe if you don't define the factors exactly correctly, maybe that's why we actually do better even than this.
Okay, but these factors are not coming from the data. This is the Fama French factors.
This one is the Fama French factors, yes. Yes, we could. We just applied all of them that they just did, yes. We actually now even have all of the non-linear shrinkage ones. And I mean, I was just amazed that, we didn't tune anything, right? We don't even have a tuning parameter, nothing at all. So I didn't expect this. I thought we'll have to work somehow, add at least some pre-knowledge of finance in, but it doesn't seem that we have to. Okay, so with that, let me just end. So I think why one should care about total positivity is because it is anyways implied by many models, like these factor analysis models, but MTP2 is weaker, but it is actually much easier to fit, right? Factor analysis, I first need to estimate the factors, then I need to do estimation under the factors. Whereas here we don't, you get like, you are actually just solving a convex optimization problem, which is super easy to solve. If you do a tree model, that's always non-convex, right? So we're kind of convexifying that constraint, so it's much easier computationally. It is a super strong constraint, but anyways, if you like tree models, it's anyways implied. As I showed, I hope I was able to convince you that it is relevant for many different kinds of applications. And it just gives you so many things for free, right? You can actually apply it in the high dimensional setting, like in the psychology data set that we saw, where you couldn't apply something else. And you just get interpretability for free because we get a lot of zeros. So we saw this psychology graph just come out for free. We can do non-parametric density estimation, just add MTP2 and log-concavity as a constraint. It seems, and here there is still a lot of research to be done, right, in terms of theory. We don't have the rates of estimation. We don't know how good the estimator is. It just seems that you need very few samples in order to get something that looks pretty good. But we don't have it. Actually, the theory worked out here, so there is still a lot to do. So I hope I was able to convince you that there are many, many different nice applications of MTP2, but it also leads to a lot of nice theory in terms of exponential families, convexity, combinatorics, and semi-algebraic geometry that I didn't really go into. Okay, so these are all the references that we have on MTP2. We really started with something where we just looked at conditional independence relations of what MTP2 implies. And this is the paper under Gaussianity. This is the paper for showing that you don't need tuning parameters in the high dimensional setting. Then this is the Ising paper. And then this is the non-parametric density estimation paper. And this is the finance paper that hopefully will be on the archive in a week or so. And with that, let me just do some advertisements. So I am building a new group at ETH Zurich, and I'm very interested in good PhD students and postdocs. So if you are interested, just email me. And also, with Shiva, we're organizing in Singapore. So I haven't talked at all about biological applications. MTP2 is something that we want to apply for estimating gene expression data in the spatial context. And we are organizing a conference on genomes and AI, in particular at this intersection between packing and expression, how machine learning and AI can come together with cell biology and genomics, which is in October in Singapore. And we are hoping that you will submit some abstracts for talks and for poster presentations. I think we have a really amazing list of speakers. So just contact us if you have any questions. Okay, and with that, thank you very much for your attention.
Are there good fast mixing, nice Markov chains converging to MTP2 distributions?
Yes, so I only know it in the Gaussian setting, and there is actually, so there's something else that we didn't really look at, which is, well, let me just not go there. So if you have an additional constraint, which is stronger than MTP2, which is diagonal dominance. So namely that if I sum up all of these entries here, then so all of these are negative, right, or smaller or equal to 0. On the diagonal, I have something positive. If this sum in every one of the rows is larger than 0, then I know that we have all of these fast mixing algorithms, etc., and you can do estimation, etc., very quickly. So that's a stronger constraint than MTP2. So we actually looked at that constraint in the non-parametric setting. So I know how to define it, even in the non-parametric setting. And what would be really nice to prove is that you actually get all of these results for any distribution that satisfies this, even in the non-parametric setting. Yes. So Ising models as well. So you have this stronger constraint that is this diagonal dominance. But people haven't looked at any other distribution. How would I define this equivalent of diagonal dominance for any distribution? And I think we have it in the non-parametric setting. But I don't know of these results how they generalize, which would be really nice to do. Yeah.
Can you also test?
Yes, it's a very good question. So no, that's one of the big questions. How do we do a hypothesis test for MTP2? Yes. Yes, so that was also the motivation for doing non-parametric density estimation, because now I can do non-parametric density estimation under MTP2 and log-concavity. I can do it under just log-concavity, and then I can do a hypothesis test based on the densities, right? How far away are they from each other? Because I can then resample from the density and see if I get something similar. But we don't have, and so the problem is, I actually have it just open here. So we don't have this result, although we conjecture, we don't have it for higher dimensions. So we can still not do hypothesis testing. So that's a really good question. Even in the Gaussian setting, how would you do hypothesis test for MTP2? For now, we're just applying it in settings where we would otherwise apply a tree model. So then we know it implies MTP2. So we're, if people are happy with trees, I would just do this.
Only consider those variables giving positive, but after looking at the sample correlation.
So actually, I wouldn't be scared of that. So because if I just apply it in a larger setting, what actually happens is all of these entries will just become zeros.
Yeah, that, but if you just selectively apply on those, then you do a selection. Don't ignore the other negative or zero.
No, but let's not ignore them, I'm saying. So we have a result which says that the covariance matrix under MTP2 is always going to be block diagonal. Okay? So either you are MTP2 and you're going to come out in this big block, or otherwise you'll just get zeros there. So they will just show up as singletons. So it will actually anyway show up. So they will not be MTP2 because they're not connected to anything else. It then makes sense to assume that these variables are MTP2. So actually for finance applications, this is how we're thinking of actually applying it to find stocks that move opposite direction, right? Very often to diversify, you actually want to find stocks that don't move up when or don't move down when everyone else moves down. So you can still just do this and find the stocks that just appear as singletons somewhere that are not connected to anything. So, yeah, you should include them, yeah. And it's nice because you'll actually just get them out as singletons, yeah. So I think it's a good constraint also for that. It's also interesting when you're not connected to everyone. Yeah. Sorry, there was another. Did you have?
You mentioned that changing the sign of the inequality doesn't imply, of course, negative association, but does it imply anything interesting still? Is that still something?
Yeah, so it implies weak forms of orthants, like being in one orthant. But I don't know how interesting it is for data science. Yeah, so it would be nice if one has, like what we had for MTP2, right? Somehow we needed like a large class of models that will imply MTP2, and then it is interesting for using it for applications. So it would be nice to know what implies that. What kinds of models imply that? And then it might be interesting to look at. I just don't know it.
I was just wondering whether the anti-ferromagnetic ones would satisfy things with the other way around.
Yes, so they would satisfy this with the other way around. Yeah, exactly.
Yeah.
But then, yeah, so just that application alone, I don't think, right?
That may not be interesting.
Exactly, for modeling, yeah. But it might be.
But anti-ferromagnetism is also, you might think it's ubiquitous in a different way, in another universal.
I see, yeah. Yeah, so maybe it would be interesting to know what you can get out of these kinds of constraints, even from a mathematical perspective. So maybe I'm more, I'm usually motivated when I see an application where, where it makes sense to apply it, yeah. But I don't know what the mathematical properties are that you would get out. For us, it was just basically everything we ever tried to prove seemed right. And that's very nice, right? So in terms of conditional independence relations, everything we ever tried to prove, which never happens for conditional independence implications, is just holds for these MTP2 distributions. That kind of tells you that it will be very nice for data analysis. But I don't know what it will be for otherwise.